So we have the functions, three variables, a, b, and c. I try to make it simple enough. It's the max terms of 2, 3, 5, and 7. Find the minimum product of sum. Design using NOR gates only. Again, save some paper. Here we go. Let's see what I have. A, B, and C. There's 8 combinations. Two zeros, 2 ones, 2 zeros, 2 ones. 4 zeros, 4 ones. So what is F going to equal to? This tells you where the zeros are. At 2, which is right here. At 3, right here. At 5, right here. And at 7, right here. That's where the zeros are. At 2, 3, 5, and 7.
Or, so it has to have at least 1 0.
Why?
No?
No. So the rest will be what? Ones. If you don't have any zeros, that means what? Your output's always going to be high. So that's when it's going to be 0. That's what F is. It's going to be ones right here at 0, 1, 4, 6. 0, 1, 4, 6. It's going to be 0, 2, 3, 5, 7. So my function here as product of sum, again, if I rewrite that, here's the first one. A, B bar, C. Product of sum, so they have to be a sum here. The next one is what? A, B bar, C bar. The next one down here, A bar, B, C bar, and the last one is what? A bar plus B bar plus C bar. So I found what the expression for it is. Now I'm going to simplify it. I got to simplify that. I'm going to use Boolean algebra to simplify. So let me just write on the normal paper now. Here we go. F of A, B, and C. The first one, A plus B bar plus C. A plus B bar plus C bar. The next one, I'm going to rewrite the next one. I'm going to shuffle them around. A bar plus C bar plus B. I decide to reverse the B here. And the last one, what? A bar plus C bar plus B bar.
So when you say find the minimum product of sum, it has nothing to do with the min value?
No, minimum means the least number of gates. Simplify, or the smallest size number of inputs.
So when you write maximum,
You got to simplify it, basically.
is maximum also simplified?
Yes.
They accepted that, so
Find the minimum sum of product. Find the minimum product of sum. Minimum means minimize your expression.
okay.
Just like in math, when you factor, simplify your answer, that's what that means. Now, these guys, we have, just in case you forgot, we have one of those Boolean algebra that says x plus y times x plus y bar. What was the answer to that one? Remember what that equation is?
Yes.
Which is what? x. You can FOIL that out, you'll see. And so if I apply that here, notice the first two here, if you look at them, it's this one, that's your x. This is your y. This is your x. This is your y bar.
No question.
Yep.
So you have a C regular C and a C bar.
Yep.
It only works that way. You can't have two C bars for that expression.
No.
No.
Yep, it has to be like this. So that's x plus y times x plus y bar. So the answer to that is x. X in this case is what? A plus b bar, right? Let's look at the other one. I reshuffled the other one for the same reason, because that's the same now. This is x. This is y. This is x. And this is y bar. And if I apply that, the same equation to that one, that's going to give me what? A bar plus C bar.
Now, what if you had had two regular B's? Would you be able to do it that way since you have two complements, A bar?
If I have what, B or B bar?
Like two regular B's instead of the B complement? Yeah, instead of the B bar.
Like if you mean like if it were A plus B plus C and then A plus B plus C bar?
No, A bar plus C bar like it is, except, in other words, would you be able to flip that around and have Y be A bar plus C bar? Because they're both complements.
If this was B bar? Yes. If this was, or if this was not a bar.
I'm looking at the right expression on the top.
Here?
The right one, yes. I'm saying if that B was, if both of them were regular B's.
Yep.
Would you be able to flip them and say Y bar as A bar plus C bar?
It's an expression.
No, because you have A bar plus C bar times A bar plus C bar.
If this was a B bar, that would be the same as this, which you can get rid of it when you have two the same.
Oh, okay.
Right? That will be the same as this. So you get rid of it and you end up with that expression. Now, when you take that with this, can you simplify it? You know, then you have to look, okay, I got this one from the first group, A plus B bar, and I got that from the other group. What can I do with it? You know? And try and find out if there's a way you can simplify it. So now there's my circuit here, and my next one, design using NOR gates only. So when I look at that, here's what I see. A, B with the NOT, going to an OR gate, right? The other one, you have A going through a NOT, C going through a NOT. And both results are what? Are ANDed together. This is what F is. And I'm saying, I don't want you using NOT gates, OR gates, AND gates. I want you to use only what? NOR gates. You design using NOR gates only. So we got to take care of that. Well, one of the things I know, that a NOT gate, I can make a NOT gate out of a NOR gate. So that's not a big deal. How do we do that? We take an OR gate and tie both inputs together. So I can get rid of the NOT gates by using NOR gates. But I still have an OR gate here. Yes, Jordan, go ahead.
So you do the same thing with another NOR, putting the output of the first NOR back into another NOR with itself. And then
You could. Or you don't have to, because now you increase the number of gates. He said, take this, put a NOR and put another NOT gate. Is that what you said?
Yep.
So basically, like, undo it. So he's saying, If you put a NOT gate, you actually complement that. If you make this a NOR gate, now that's the complement. So what Jordan's saying, put a NOT gate here, which is one of those gates, but you still have the AND gate now. But you're on the right track, because what you're trying to do is double complement that so it doesn't change the value. So by making that a NOT gate, I just flip that, so I need to flip it again. You're right, I need to put a NOT gate. So let's put the NOT gate right here before you feed to that AND gate. And do the same gate. Same thing to this gate. Double knotted. So now both of these are what?
NOR gate.
NOR gates. So I'm okay so far. Here we go. We're making progress.
They have to be NOR gates.
Yep. Now they're NOR gates because I said I want to use NOR gates only. So what about this gate? This gate right here.
It's an AND gate.
It's an AND, but both inputs are complement. Input, not output. If it was the output complement, that's an AND.
So you can flip it over, and, right,
To what?
to a NOR gate
Why?
because of what's it called? The Morgan's rule.
Yep. He said, De Morgan's theorem says if you have,
Complements.
that's a NOR gate, right? A or B complement that. That's equal to what? A complement and it with B complement. So what that means, I'm not sure why the A is capital and the B is lowercase, but if you have an A and a B, that's equivalent to an AND gate. You complement that, complement both inputs, and that's what this one represents. This one represents an AND gate where both inputs are complemented. That's equal to a NOR gate. Now we design the whole thing using NOR gates only. And the same thing with NAND gates. We have another De Morgan's theorem for the NAND gate. It says A and B not is what? A not or B not. You can make a NAND gate A and B. That's the same as an OR gate with both inputs being complemented. So if you complement both inputs to an OR gate, that's equivalent to a NAND gate. You complement both inputs to a NAND gate, that's the same as a NOR gate.